This is lecture 22, and we're going to be talking about L'Hopital's rule. L'Hopital's rule has to do with calculating limits. So we're going back to this idea of how to calculate the limit of a function. But it's a limit where we have a hard time figuring it out because it's bad news. L'Hopital's rule gives us a way to do that. The reason we're looking at it right now is that we're in the middle of getting information about functions so that we can graph them or so that we can get an idea of what they really look like. One of the pieces that's missing that the derivative doesn't tell us too much about is what is the behavior of a function as x gets very, very large, or what would be the ultimate fate of some phenomenon if you let time go to infinity, or as you get close to some place where there might be a vertical asymptote, what happens, or what happens where you might have a discontinuity. So in other words, the limit is what you need in order to fill out the picture of what the function looks like. Anyway, we'll look at that in another couple of days. But for now, what I want to focus on is what L'Hopital's rule is. By the way, our textbook mentions that it talks about this as L'Hopital's rule, but spells it Hospital and says that the guy himself spelled it that way. I have seen more people spell it with the O circumflex. That's that little hat on the O. And in the French language, that historically denoted that at some time there was an L, or an S rather, and it just got dropped and they just have an O with a hat on it. In any case, I will spell it that way undoubtedly. You can spell it however you like. It doesn't make any difference. People will know. All right, so we need to talk about what L'Hopital's rule is, where it applies, and what it's good for. Okay, L'Hopital's rule allows you to calculate a limit of a fraction. So we're looking at a quotient of two functions. So you think about f of x divided by g of x. And L'Hopital's rule deals with the bad news situation of what happens when the numerator and the denominator, the top and the bottom, both go to 0 or they both blow up. So f of x goes to infinity, and this can be plus or minus, it really doesn't matter. And g of x goes to infinity. And see, the problem is that when you are forming a quotient like this, let's take a look at the 0 over 0. This is a 0 over 0 situation. We've talked about this before. When you have a 0 over 0 situation, that's bad news because the numerator is trying to drag the fraction to 0. The denominator, by getting small, is making the fraction get large. So you've got a battle going on here, and it's hard to tell what's going on. We learned some tricks for dealing with this, but there are a lot of problems where none of those tricks that we dealt with, that we had, is going to help too much. Same thing happens here. When f and g are both blowing up, you've got an infinity over infinity situation. Now, I'm not saying that these are numbers. I'm saying that the numerator and the denominator are getting large. And so if both the numerator and denominator are getting large, this is bad news because the numerator is trying to drag the fraction off to infinity, make it bigger. The denominator, by getting bigger, is making the fraction get small. And so you've got a battle going on between these two, and it's not possible to just look at it and tell what's going on. So this has been bad news. Once again, we've had tricks for helping us do this, but those tricks don't work in all cases, and now we have to look at lots and lots more examples where none of the tricks that we had before are going to work. L'Hopital's rule is not exactly the weapon that makes you invincible. It's not going to solve all of the problems of limits where you've got 0 over 0 or infinity over infinity, but it is going to solve a lot of them, and you need to know how to use it and when it applies. The first rule that you have to know about L'Hopital's rule is that it only applies to these two situations. If you do not have a 0 over 0 or an infinity over infinity situation, L'Hopital's rule does not apply. You can't use it. So let me do an example of that first. Here's a situation where a lot of people might use L'Hopital's rule. Suppose you're trying to calculate the limit of sine x over x. All right? And you want the limit as x goes to infinity. Now, the first thing that you should do whenever you do a problem involving limits is to do the reality check that I've been telling you to do. Ask yourself what happens to the top and bottom as x goes off to infinity or goes to whatever it goes to. In this case, the numerator is the sine of x, and it's just going to oscillate back and forth between 1 and minus 1. On the other hand, the denominator is getting bigger and bigger. So the numerator doesn't even have a limit. It's going back and forth between plus and minus 1, and the denominator is going to infinity. So this is not a 0 over 0. This is not an infinity over infinity. L'Hopital's rule does not apply. And if you tried to use L'Hopital's rule, you would get into problems. You would get into trouble. So L'Hopital's rule just doesn't tell you. Now, actually, this is something where we can tell what's going on very, very easily. If the bottom is getting big and the numerator is bounded by plus and minus 1, the numerator is not doing much about it. So the denominator rules and drags the fraction to 0. So, in fact, the answer is 0. So really, if you have a fraction and it's not one of these two cases, you really already know what the answer is. There's an easy answer, and you can just determine it by seeing what happens to the top and what happens to the bottom. Okay, so what does L'Hopital's rule say? So if we're not dealing with this kind of stuff, if you are dealing with a 0 over 0 or infinity over infinity situation, L'Hopital's rule says this. Well, let me write it out. If the limit, all right, let's say, if f of x over g of x is an infinity over infinity or 0 over 0, and we call these things indeterminate forms. Indeterminate. If f of x divided by g of x is one of these two types of indeterminate form, then the limit of f of x over g of x turns out to be the same as the limit of the derivative of f divided by the derivative of g. Now, that doesn't tell you what the answer is. It tells you that you traded this problem for this one. So let's look at an example where that's actually very useful. And it's one that we've seen before. Take the limit, not as x goes to infinity, but the limit as x goes to 0 of sine x over x. Now, I proved this already at great length with geometry and trigonometry, that the limit of this is equal to 1. But let's just do it with L'Hopital's rule right now. L'Hopital's rule says that if you've got a 0 over 0 indeterminate form or an infinity over infinity indeterminate form, then you can calculate the limit by calculating the limit of the derivative of the top over the derivative of the bottom. Notice this is not the quotient rule. This says take the derivative of the top and the derivative of the bottom, and the limit that you get will be the same as the limit of what you started with. Okay, what are we dealing with here as x goes to 0? Obviously, as x goes to 0, the bottom is going to 0. What about the top? As x goes to 0, the sine of 0 is 0, so the top is going to 0. So this is an indeterminate form, a 0 over 0 situation. L'Hopital's rule applies, and therefore, the limit as x goes to 0 of sine x over x must be the same thing as the limit as x goes to 0 of the derivative of sine x, which of course is cosine, divided by the derivative of x, which is 1. And now we need to see if we can calculate this limit. Well, do the reality check. As x approaches 0, nothing happens to 1, and the cosine of x is just getting closer and closer to the cosine of 0. Cosine of 0 is 1, so the answer is 1 over 1, which is 1. And we already knew that, because that's what we got for the limit of sine x over x. Of course, x measured in radians, but that limit is 1. All right? So L'Hopital's rule shows us an easy way to do that limit that took us forever to do. Now, by the way, I haven't proved L'Hopital's rule, and we're not going to do that in this class. But the proof of L'Hopital's rule is, well, it's not too bad, but we're not going to take the time to do it. All right, let me do some other examples. let's try, that wasn't very good. Let's try the limit of the natural log of x divided by x minus 1. And we're going to take that limit as x approaches 1. Okay, first thing that you always have to do is a reality check. What's happening as x approaches 1? Well, bottom, of course, goes to 0 as x gets close to 1. What about the top? As x goes to 1, log of x is going to log of 1, which is also 0. So, yeah, you have a 0 over 0 situation. L'Hopital's rule applies. So the limit of this quotient is the same as the limit as x goes to 1 of the derivative of the top divided by the derivative of the bottom. The derivative of the log of x is 1 over x, and the derivative of x minus 1 is easy, that's 1. Okay, so simplify this, that's easy. Limit as x goes to 1 of 1 over x. Once again, check out, do a reality check here. As x approaches 1, nothing happens to the top. As x approaches 1, x approaches 1. So this is not bad at all. The answer is 1. So we have an answer for this limit using L'Hopital's rule. Okay. I think at this point, let's take a little bit of a break and see something completely different. Okay, well, that's something that you may want to remember for the quiz, but don't tell anybody. Don't tell anybody who is not watching videos. You want to gain a few extra points over other people. All right, let's look at another example. These are simple examples of L'Hopital's rule. This one is not quite so simple. We want to look at e to the x over x squared. And the question is, what happens here as x gets large? As x goes to infinity. Do your reality check. As x gets large, e to the x, of course, goes to infinity. As x gets big, x squared, we know, gets big. So we have an infinity over infinity. Now, this is one of those situations where you might say, well, e to the x grows faster than x squared. Well, how do you really know that? You know, it just may look like it, but do you really know? Well, L'Hopital's rule gives you a way of answering this question. And so all you have to do is say, since we're dealing with infinity over infinity, L'Hopital's rule says the limit of this is the same as the limit of the derivative of the top divided by the derivative of the bottom. The derivative of e to the x is e to the x, and the derivative of x squared is 2x. Time to do another reality check. What happens to this as x gets large? Well, the numerator is still going to infinity, but 2x is also going to infinity, so we still have an infinity over infinity situation. Well, L'Hopital's rule still applies. So you calculate L'Hopital's rule, the derivative of the top and the derivative of the bottom once again. And you get e to the x still on top and 2 on the bottom. This time, your reality check shows the numerator is blowing up as x gets large. The denominator does not. So here's a fraction where the numerator is getting big and the denominator does nothing about it. Therefore, the answer is infinity. And that corresponds to what you know intuitively. E to the x grows much faster than x squared. Okay, so L'Hopital's rule tells us that. And it took us 2 applications of L'Hopital's rule to see this. Which brings up an interesting point. We've already known how to do these kinds of problems for things like this. What's the limit as x goes to infinity of 4x to the 7th minus 3x to the 5th minus 2x plus 17 over 3x to the 7th plus 4x to the 4th minus 3x squared plus 2. Well, one way to do this problem is to say, well, as x gets large, x goes to infinity, top and bottom are both getting big because of that x to the 7th, and so L'Hopital's rule applies. And you can just imagine what's going to happen. You take the derivative of the top, you're going to get a 6th degree polynomial, same on the bottom, both of which are still going to blow up, and you can apply L'Hopital's rule again and again and again. You're going to have to apply L'Hopital's rule like 7 times to get it down to something where you'll know what the answer is. But we already did these kinds of problems in one step. You multiply top and bottom by 1 over x to the highest power. And when you get done doing that, let x get big. All the stuff here goes to 0, and you're going to be left with 4 and 3, and so the answer is 4/3. All right? So this is one of those situations where L'Hopital's rule applies. You do have infinity over infinity. That's not the problem. The problem is it's stupid to use L'Hopital's rule in this situation because there's a much easier way of doing the problem. So you don't. Okay, so to summarize, don't use L'Hopital's rule when you already know how to do the problem. Don't use L'Hopital's rule when you don't have one of these indeterminate forms, when you don't have 0 over 0 or infinity over infinity. If you have anything else, you should be able to do the problem. If it's a fraction that's not one of these two things, L'Hopital's rule does not apply, and you should already know the answer. You know, for example, what if it's a 17 over infinity type of situation? In other words, the bottom's getting big and the numerator gets close to 17. The answer is this is 0. Right? We just saw an example where the numerator is big and the denominator was some constant. The answer is it blows up. Okay, we could go to something over 0. If it's not 0, then this is going to blow up. This will be infinite. If it's 0 over something else, that's going to go to 0. So we know how to do any of the problems where it's not bad news. These are the bad news. And L'Hopital's rule tells us how to deal with them. And there are going to be examples where it's going to take some doing to figure out how to use L'Hopital's rule to apply to the problems. But for now, this is just the easy introduction to L'Hopital's rule. Notice at the beginning also, I didn't even say the limit as what happens, because whatever it is causes this infinity over infinity or 0 over 0. So that is whatever it is. So if it's x approaching 0, x approaching 1, x approaching infinity, whatever it is that makes numerator and denominator both blow up or both go to 0, then that's what you're dealing with, and L'Hopital's rule applies. Okay, so that's about it. This is the introduction to L'Hopital's rule. There are a lot more problems in this section that we'll cover on Wednesday when we talk about how to use L'Hopital's rule in much more complicated situations where it doesn't even seem like L'Hopital's rule could possibly apply. But before we can do that, we should be comfortable with using L'Hopital's rule for lots of problems where it does apply. All right, that is it for now.